So welcome back. In this lecture, we're going to start talking about the variable elimination. It's a popular algorithm for inference in Bayesian networks. So in this lecture, we're going to learn about our first inference algorithm, and it is one of the simplest methods for inference in Bayesian networks. So it uses the idea of marginalization. We can remove variables that are not included in the query in order to answer that query. We identified 4 different types of queries, and you're going to see that variable elimination can be used to answer any of them, but now we're going to focus on 2 of the queries, and I'm going to leave MPE and map queries to a future lecture. So we're going to discuss the algorithm of a variable elimination. We're going to discuss a little bit how to improve its complexity by smartly choosing the order of the variables that I'm going to eliminate. We're going to discuss one variant that is called bucket elimination, and that's going to prepare us for the tutorial. Then we're going to implement this and see how it works in practice. So let's try to understand the variable elimination algorithm by using one example. So we have this Bayesian network, structure and all the parameters, and let's suppose that we are interested in this probability of D and E. So this is going to be the final result for our computation, and we can see that this information is not readily available in the network. So if you look at the parameters, we're not going to find the probability of D and E. So we have to make an inference process where we're going to convert those numbers into the probabilities that we are interested. The way of doing this in a very naive approach is to compute the joint probability distribution. And we know how to do that because looking at the network, we can figure out what's going to be the factorization for the network. So we use the chain rule for the Bayesian networks, and we can compute the full joint probability that involves all the variables. And eliminating the variables that we are not interested, the ones that are not part of the query, we can compute probability of D and E. But this naive procedure is going to be exponential in the number of variables, so it's not very efficient. So the variable elimination algorithm is a little bit smarter. We're going to see that we can eliminate the variables earlier in order to not have or to try to avoid this exponential time computation. So let's take a look at how we're going to do this using the naive approach. So in the naive approach, what we do is first to compute the full joint distribution, the joint distribution over all variables that we have in the network. So we know that we have 5 variables, A, B, C, D, and E, and I compute the full joint distribution here for you. I have to split the tables in 2 sets because it was too big to fit in these slides. So, but here we have the joint distribution for all variables A, B, C, D, and E, but we are only interested in the probability of D and E. So what we have to do is to eliminate the variables A, B, and C one by one until we get just the probability of D and E. And the process of eliminating the variables that we call the sum out variable X, for instance, sum out variable A, is a summation. So we saw this before. It's we also call that this process marginalization, and it's actually very simple. What we do, we look at the rows. We look at the rows that match the assignments between all the variables that are going to keep, and we sum for the values of the probabilities. So we look at here. Let's suppose that we're going to sum out the variable A. So we look at for variables B, C, D, and E. So we have all true values. We look for another row that we have true values for B, C, D, and E, and we're going to sum these 2 rows. So we see that we are summing for all possible values of A. So A is a Boolean variable, so we have A and not A. And so this is the process of summation. So we're going to sum this probability with this probability here, exactly what we have here. And if we do that for all possible assignments that match, so we're going to do for this assignment here, we're going to sum with this one here, look at that exactly the same assignment, and we sum over all possible values of the variable A. We're going to have a smaller table that does not mention A. So at the end of this process, we're going to reduce this table that has 32 entries into a table that has only 16 entries and do not match variable A. So an important property of summing out the variables is the fact that the distribution that we get is as good as the original distribution for answering queries that do not involve the variable that we eliminated. So in a more concrete way, that if we have this distribution here, p prime alpha, and this is the distribution that we got after we eliminated one variable, for instance A, it will give us exactly the same probabilities that we had before. So this is the original probability distribution. So it will be exactly the same probability for every event alpha that does not involve the variable A. So if you are interested in the probability of D and E, what we have to do is to eliminate the variables A, B, and C from the joint distribution. The problem of this procedure is that we are building the full joint distribution over all possible variables, and that is going to be exponential in the number of variables. So it's very expensive to do that in terms of computational time. But the variable elimination algorithm does is slightly different. So we can sometimes escape from this exponential complexity by not computing the full joint distribution. So we're going to try to anticipate a little bit the elimination of the variables so we don't have to build the entire joint distribution. Before we get into the variable elimination algorithm, let's first discuss what we call factors. So factors is a function over set of variables. In some way, it's going to be a generalization of our idea of prior and conditional probability tables. So technically, a factor is a map for each instantiation of the variables into a non-negative number. So in most cases, we will be dealing with probability distributions or conditional probabilities. So in this case, our factors will represent those tables. So we can have, for instance, one factor like this, and this is a conditional probability table, is the probability of D given BC. And we can see that it's not probability distribution because those values here do not sum to 1, right? In other case, we do have a probability distribution. In this case here, we have the probability of D and E. So we see that they do sum to 1. In some cases, we have over an empty set of variables. In this case, we call it the trivial factor. So the trivial instantiation will be represented by this symbol here that reminds T. So it's going to be a map between this trivial instantiation and the number. And we're going to see that sometimes this number is not a number between 0 and 1 as we are used to in the case of probabilities. There are two operations that we do over factors that are very common. One is summing out a variable, that is what we have already seen in the previous slide, and I'm going to formalize this a little bit better. And the other one is multiplying two factors. And these two operations will be the building blocks for many of the inference algorithms that we're going to study in this course. So let's start looking at summing out a variable. The summation is the process of eliminating variables from a factor. So let's suppose that we have a factor f that is defined over a set of variables. If you want to eliminate one of those variables, we create a new factor that will have a domain that does not include the variable that we eliminated. So it's going to be a new domain y. It has all the variables that we had in the original factor, but the one that we want to eliminate. And we can denote this new factor by sigma xf, illustrating that it passes through a process of summing over the values of the variable x. So just to illustrate this process again, let's suppose that we have this factor here, f1, and we want to get the variable d eliminated. So the resulting factor is going to be this sigma d f1. So we can see that the process is very simple. It's a matter of matching the instantiations for the variables d, b, and c. So we have here b and c matching, and we sum these two values here, and we get as a result this first entry of the second table. And we see that we are assuming over all possible values of the variable d in this case. And the same thing is going to happen here, here, and here. And we can see that the resulting factor has a value 1 for all possible assignments. And we can continue doing that, so we can eliminate the variable b, we can eliminate the variable c. If we do that for all variables that we have, we will get what we call the trivial factor. In the trivial factor, it has a trivial instantiation here and assign it to the trivial instantiation a number. In this case, the number will be 4, right? So it's going to be the summation of all those ones here is going to be 4. So we can see that the number does not need to be a number between 0 and 1 as we have in the probabilities. The number associated in the factor can be even larger than 1. So one interesting property of summation is the fact that it is commutative. So it doesn't matter the order that I'm going to eliminate the variables, the results are going to be the same. So if we want to eliminate two variables, x and y, we can first eliminate x and later on eliminate y, or we can eliminate y first and after that x. The results are going to be the same. In terms of numbers, we're going to be exactly the same numbers. So we can use a notation that we say the summation of a set x. So see that this x here is in boldface, indicating that is a set. And in this case, we have to eliminate the variables in the set. It doesn't matter the order they're going to be, the results are going to be the same. So in order to formalize this idea a little bit better, we can introduce an algorithm for that, and we have this algorithm here. So we have an input and factor f that has a domain x and also a set z of variables that we want to eliminate. And the output is going to give back the summation over the set z of the variables that are in the factor f. So the domain of the resulting factor, we're going to call it y, and it's basically the set x minus, so we're going to removing the variables z of the set x. So it's going to be a set that has all the variables that we had in the original factor minus the variable z. We're going to start creating an f prime, a factor over all the variables y, and with 0 probabilities. So we are creating an empty factor for all possible instantiations of y with 0 probabilities for every entry. And these two for's here, you're going to do the process of summation. So we take every possible instantiation y. So for each possible instantiation y, so it's going to be each entry into the resulting factor. We're going to look for all possible instantiations z. So these instantiations z are the variables that we are eliminating. So we are summing over all possible combinations of values of z and doing the summation process. Okay, what's going to be the complexity of this algorithm? And it's going to be exponential in the number of variables that we have in the factor. So we're going to represent this as this. So this exponential in the number of variables is because the original factor had this property, right? So it had this size exponential in the number of variables, and the algorithm must operate over this factor. So you're going to scan this factor, you're going to look for all possible entries in this factor, you're going to sum them in an appropriate order. So it's very clear that we have to go through all the entries in the original factor. So if the original factor has exponential size, so the algorithm also has exponential size. So this complexity is going to be for also time and space, because we have to store the original factor in the algorithm in order to make the computation. So we call this operation marginalization, and we also say that this marginalization operation is a sort of a projection of the original factor that we had before eliminating the variables into a new set of variables y. And the second operation over factors is known as multiplication. And in some sense, multiplication has the reverse effect of summation, because when we are doing summation, we are eliminating the variables. So we are making the factors, the resulting factors, smaller and smaller. But when we do multiplication, we take two factors and multiply one by each other, the result factor will have a set of variables that are the union of the variables that we had in the first factor and the second factor. So let's try to explain this using one example. And let's suppose that we have these two factors here, f1 and f2, and you want to compute the multiplication of f1 by f2. So the resulting factor will have all the variables that we had in f1 plus the variables that we had in f2. So f1 we have b, c, d, f2 d, e. We're going to have b, c, d, and e. So b, c, d, and e. So this is the union of the variables in f1 and the variables in f2. And how I compute the resulting probabilities, so it's going to be the multiplication. So we take one entry here. So it's very important that that's going to be a table where we have all possible combinations of B, C, D, and E, so all possible assignments. So I take one assignment here, it's going to be true for all variables, and we'll locate the matching assignments in the two tables. So B, C, and D true we have here, and D and E that are true we have here. So for this first row, we're going to have to multiply 0.95 with 0.448. So right here, so this is the resulting probability. For the next row, we're going to have to look for one assignment that is B, C, D, and not E. So B, C, D again is the first row here, but now D and not E is the second row. So we have to multiply 0.95 with 0.192. So we have this row here. This is the resulting probability. One more. We have this assignment here. B, C, not D, and E. So now B, C, and not D is the second row. And we have a not D and E. Not a D and E is going to be this row here. So we have to multiply 0.05 with 0.112. We have the result in this here. So we continue doing that for all entries that we have in this table, looking for the compatible assignments that we have here and the compatible assignments that we have here, and we multiply the entries, and we're going to have the final result. It is interesting to note that for each instantiation that we have in the resulting factor, we're going to find exactly one instantiation that's compatible in each one of the factors. And this multiplication operation is commutative and associative, so we can multiply several factors without specifying the order of the multiplication. So it's going to be similar to the summation. So we can create an algorithm that multiply a certain number of factors, like m factors together, and get into a resulting factor. So exactly what we have here, this is the algorithm. Then we'll take m factors and multiply them all together. So this input is going to be the m factors. They're called f1 to fm. Each one has a domain that's called x1 to xm. And as a result, you're going to have a factor that is the multiplication of these m factors. So we start computing what's going to be the domain of the resulting factor. So what are the variables that will be in the resulting factor? And we call this z. So it's going to be the union of all the xi sets. We create a new factor f, and this factor is a sort of a factor in which we have ones for every entry. So it's going to be over the variable z, that are these variables that we just computed, and all entries have a value 1. And we start doing the multiplication. So we will need two for loops. The first for loop will be for each instantiation z. So we can think as this first for loop as going through each entry of the resulting factor, and this internal loop here will do the multiplication. So as we have m factors to multiply, so I'm going to be a loop for a variable I 1 to m. So we're going to go through all of the factors. We're going to find an instantiation xi that is consistent with z. So remember that z is a larger instantiation, so we need to find a subset of this instantiation that is compatible with the first factor f1, and I'm going to multiply whatever we have in the result factor that is initially 1 by the number that we have in the compatible instantiation in the factor f1. And we do that for f2, f3 until we get into fm. And that is the resulting factor that I'm going to return as a result of this operation. So what is the complexity of this operation? And it's clearly proportional to m exponential in w, where w is the number of variables in the resulting factor. So yeah, that's we can understand why that happens, because we are going through every entry of the resulting factor and computing m multiplications for each of the entries. So as we have exponential number of entries, and this exponential is exponential in w, so we have this complexity that's m times an exponential in w. All right, so I guess that is enough for this first video. Now we're going to have to understand how we use these two operations over factors, summation and multiplication, in order to get the variable elimination algorithm. But we're going to do that in the next video.